Do objects unstretch when a load is removed the same way they stretch when the load was first brought up? Let me rephrase. You've already learned how to plot force extension graphs by adding weights. Now would the graphs look the same if you were to repeat the experiment, but this time remove the weights instead of adding them? Now the answer here isn't very straightforward. And in order to understand the answer, we first need to understand the concept of strain energy. Now we've learned in the previous units, when we stretch something, we do work against it. And in that process, transfer energy into it. Now here, as long as the elastic limit isn't crossed, this energy is usually stored as elastic potential energy and released as kinetic energy when the object is released. Now the area under the force extension curve represents this strain energy, which can also be calculated using its formula as follows, where F is the force applied and X is the extension of the object. For a wire, we can also find the energy stored per unit volume, and we do this by dividing the energy stored by the volume of the wire, which is its cross-sectional area multiplied by the length of the wire. Now this is pretty much the same way you would find the volume of a cylinder, and it gives us an expression that looks like this, where A is the cross-sectional area of the wire and L is the total length of the wire. Now because we know that force per unit area is stress and extension over total length is strain, we can rewrite this expression as a combination of stress and strain. Now why is that important? Well, because the amount of energy an object stores as it stretches depends on its volume. A thick wire can store more energy as compared to a thinner one. And in the same manner, a longer wire stores more energy than a shorter one. Now this ability to store and release energy is key to understanding how different types of materials behave when being stretched by adding a load versus when being unstretched by removing a load. And we can visualize this in force extension graphs by drawing them first in loading or increasing weight conditions and then unloading or decreasing weight conditions. Let's say we do this for a metal wire. We'll see that as long as the elastic limit isn't crossed, the loading and unloading curves are essentially the same. This is because metal is really efficient at storing and releasing elastic potential energy. So almost all the energy stored while loading will be released while unloading. Although this isn't the case if the elastic limit is crossed. As we'll see in the loading and unloading graphs for metals where the elastic limit is crossed, the energy put into the wire while loading is greater than the energy released while unloading. And this is because some of the energy is used to permanently deform the metal, and as a result of that, it can no longer be released. Things are really different with rubber though. If you were to conduct the same experiment with a rubber band, you'll get two distinct curves for when the band is being loaded or stretched versus when it's being unloaded or unstretched. So, let's say you have two identical rubber bands. One at 5 newtons of force, the other at 9 newtons of force. You add 2 newtons to the loading band, that is the band with 5 newtons of force, and remove 2 newtons from the unloading band, that is the band with 9 newtons of force. You'll see that the two bands are not stretched equally, even though they both carry the same weight of 7 newtons. And this happens even if you stay within the rubber band's elastic limit. This difference is because the rubber band releases less energy than what was used to make it stretch. That is, energy gained while loading will always be more than energy released when unloading. And this is true even though the rubber band comes back to its original shape. The reason for this has to do with rubber's internal molecular structure. Rubber absorbs some of the energy added to it as elastic potential energy and only releases a part of it as kinetic energy. That's why constantly stretching and unstretching rubber can cause it to heat up, something squash players are really familiar with. Alright, last example, promise. We're going to look at polyethylene. You know, the thing that's used to make plastic shopping bags? Now this has a really low elastic limit, meaning even the slightest of stress can cause it to deform permanently. So if you were to conduct a loading or unloading experiment with polyethylene, you'll get a graph that looks like this. Once again, the energy put into stretching polyethylene is way more than the energy released when the stress or weight is removed. And this is because it consumes much of the energy put into it to undergo plastic deformation and change the shape permanently. And only a small amount of the original energy is returned as kinetic energy. Understanding the different properties of different materials and how they behave under stress and strain is really important to know. Because this is exactly the type of information that engineers will need to design springs and other components that may need to store and release energy. For example, now you know that if you want something to absorb impact, rubber is a great material to use. But if you want to deflect the impact, you might want to go with the metal spring. By understanding how much strain energy a material can store, we can design better and safer components.